we're beginning the process of working through more lengthy problems of computational physics. We've done a Python coding week. We've completed a data science week. We illustrated examples in the coding week and the data science week with problems of differential equations that we're going to learn how to solve numerically, many probability problems that we're going to learn how to solve numerically, and model building. That is an important point of computational physics. So that's the background, and now we can get on to lengthier modules that tackle in detail more complicated physics problems. The first one is going to be a focus on mathematically a general method for solving differential equations, ordinary differential equations. They might be linear differential equations or nonlinear differential equations, but we're going to explore the methods for solving ordinary differential equations. Our main example, overarching example, will be the equation of motion, which is a second-order differential equation in the position of the particle. We're going to look at examples of motion involving, in today's class, we'll work on projectiles. In the next classes, we'll work on pendulum oscillators, and we'll explore how numerically you can solve a lot of problems that you can't solve analytically, where you can only find certain solutions. We'll discover the emergence of a lot of interesting motion, a lot of richness in motion. For example, chaotic motion that comes out of the numerical solution of the differential equations associated with equation of motion and these situations, for example, falling bodies, for example, pendulum motion. So that's the background. This is just a slide that's our sort of launch pad, our reference point, which was that general physics example, a very basic solution of the equation of motion of a falling body. Is constructed out of the law of motion and the law of gravity. That law of motion and law of gravity together form a second-order differential equation. We can analytically, straightforwardly solve that second-order differential equation. It's this little quadratic in time that specifies the trajectory of the falling body as a function of time, the distance traveled as a function of time. So we're going to learn how to explore this numerically, but more importantly, we're going to learn how to explore more complicated situations of falling bodies and projectile motions numerically, where there is additional forces, specifically viscous or drag forces. So the next few slides are just to introduce us to drag forces, the importance of drag forces, the effects of drag forces, and the modeling of drag forces. So the bullets on this slide, I'll just walk through them one by one. So basically, a drag force is a force that opposes the motion of some object. So a car traveling through air experiences a drag force. A cyclist cycling through air experiences a drag force, and a falling body will experience a drag force due to the moving through the air. So the air is an example of a fluid. This could be motion through water too, and both those situations called drag forces. So that's what a drag force is. It's in all the situations in almost all the situations in nature, it's opposite the direction of motion, although it's not absolutely always opposite the direction of motion. It's importantly, it's a function of velocity. So it depends on the velocity of the motion. And that makes the differential equation describing the motion a more complicated differential equation, because now we've got a force depending on velocity. Motion of a car is an example one, because important one, because the drag force is proportional to the square of the velocity of the car. So as you increase the speed of the car, it requires increasingly large amounts of power to go at higher and higher speeds, because the drag force is just not increasing linearly, but it's actually increasing quadratically. We'll talk about two approximations, two categories of drag force. We'll talk about linear drag force, and we'll talk about quadratic drag force. The names speak for themselves. So linear drag force means the drag force is proportional to the velocity, and the quadratic drag force, the drag force is proportional to the square of the velocity. Linear drag force is associated with laminar flow and a streamlined flow of the fluid around the moving object in the air or the water. Quadratic drag force is associated with the turbulent flow of the fluid around the object that's moving as the object moves through the fluid. So that's the quadratic case. Linear drag forces are most typical when you have slow motion of small particles. So a dust particle falling in air under gravity would experience a linear drag force. Quadratic drag forces are most likely when you've got a larger object moving at higher speeds through a fluid. So a golf ball, by comparison, much heavier, more massive, much faster, that experiences a quadratic drag force. So those are two, a dust particle, linear drag force, a golf ball, quadratic drag force, are kind of classic examples. I put a few more notes here. I won't go through all these new notes. Down here, I actually wrote down the masses and the sizes of a few particles, dust particle, golf ball that we talked about, and a raindrop that's somewhere in between. I computed the linear drag forces and the quadratic drag forces for those three situations. And if you do that, you can show that the linear drag force dominates for the dust particle, the quadratic drag force dominates for the golf ball, and the raindrop, well, it's somewhere in between with a role for both linear and quadratic drag forces. Here are the expressions that I use for the linear drag force and the quadratic drag force. So they're just simple formulas where these coefficients B and C just depend on the particle that's moving through the fluid. So it's determined by the particle's mass, size, shape. It's determined by the fluid and its viscosity. So that's all embodied in these coefficients here. The minus signs is just a reminder that these drag forces are going to oppose the motion, and then the V's or the V squared are just the linear quadratic dependence. Drag forces are a huge or enormous topic in computational physics, in engineering. So if you design a car, or you design an aircraft, or you design a spacecraft, you're going to be worrying a lot about drag forces. Drag forces become complicated when around the transition from subsonic motion to supersonic motion. So in a fluid, there's a characteristic speed for air. There's the speed of sound in air. For other gases or fluids, there's a characteristic speed, which if you cross, there's kind of in air, we call it the sound barrier. And that's a very complicated region of drag forces that is only amenable to computational physics. Okay. So next two slides, one is for say a few more words about the linear drag force, the dust particle slowly falling towards the ground, and then one about the quadratic drag force and the golf ball flying rapidly through the air. So in the case of the linear drag force, then the ordinary differential equation that's built out of gravity, drag as the force is, and the equation of motion as the framework is this little equation up here. It's just got this additional term from the drag force. And again, it's linear, and this is a coefficient that determines whether the drag force is large or small. Just drag force just scales with that coefficient. So as soon as you add that ingredient, you've got a new differential equation. You've got a new problem to solve. This differential equation is kind of readily solvable analytically. You don't need computational methods to solve this problem. What you discover is, let's just take the simplest case where we take an object, a dust particle, and we drop it in air towards the ground. So it's just one-dimensional motion, vertical motion towards the ground. It's just released from rest towards the ground. Then the solution for the velocity, which is what I've written down. I didn't even write down the solution for the position of the dust particle, but I wrote down the solution for the velocity. It has this form here that comes out of the analytical solution of the ordinary differential equation. This dt is the terminal velocity. So there's a new phenomenon, right? The dust particle doesn't keep accelerating towards the ground, but the dust particle reaches a terminal velocity, a constant velocity towards the ground. And this time dependence of the velocity, which is in this term in parentheses here, is just saying that there's a time constant, I've called it tau, that it represents how quickly or slowly the dust particle will acquire that terminal velocity. So if tau is large, then it's going to take a longer time for the dust particle to reach terminal velocity. Tau is small, a shorter time to reach terminal velocity. And the expression, you can write down a simple analytical expression for the terminal velocity and the time constant. The expression for the terminal velocity is easy to obtain if you just equate terminal velocities when gravity and drag are equal and opposite. So you equate gravity and drag. And if you equate gravity and drag, you get this little equation here that says the terminal velocity grows as the mass grows. So if a dust particle is heavier, higher terminal velocity, it shrinks as the coefficient of drag grows. So if the air is stickier or more viscous, then that will shrink the terminal velocity. All those things make sense. We're going to solve this problem numerically. We're going to write some code to solve this numerically. And in particular today, we're going to write the code to solve this problem numerically, but write it in a way that we could solve any ordinary differential equation numerically. So we'll try and write a code that's easily changeable to not just this problem, but any problem. The situation is more complicated if you don't have this. I asked you to imagine one-dimensional motion of the dust particle towards the ground. But if it was two-dimensional motion of the dust particle towards the ground, we threw it. It was like a projectile heading towards the ground. That's actually a much more complicated analytical problem. In the absence of air resistance, you can separate out the motion in the horizontal and vertical directions. In the presence of the drag force, you can't separate out. It's a coupling between the vertical and the horizontal motion. And so that complicates the analytical solution to a projectile with a linear drag force. And so it becomes a non-trivial analytical problem. This is the case of quadratic drag associated with turbulent flow rather than linear drag and laminar flow. This is for heavy objects at higher speeds rather than small objects at low speeds. Now we got yet another differential equation. Again, it's just built out the fact we've got two forces, drag force, gravitational force, and the foundation of Newton's laws of motion. And you put all those things together and you get this little differential equation here with this velocity dependent term over here on the right-hand side. This is a harder problem to solve analytically, but you can solve the problem analytically of dropping a golf ball in air and experiencing the quadratic drag force. This is the solution for the velocity. I haven't written down again the solution for the position of the functional tire. So this is just the solution for the velocity, where we've imagined dropping the golf ball towards the ground. It's in this solution, Vt is again the terminal velocity. So that's the velocity the golf ball will release if dropped from Patterson office tower or whatever. This term here involving the hyperbolic tangent, that's the time dependence of the velocity built into this term here, because you see the t here. And I don't know if you remember what hyperbolic tangent looks like. But it is a function that goes from 0 to 1 when the argument is large, over some, in this case, period of time, the variable inside the hyperbolic period. So what we're seeing here, that instead of the velocity evolving exponentially towards the terminal velocity, which is the case for linear drag, here the velocity evolves as hyperbolic tangent of time towards the final terminal velocity. So it is an evolution in both cases, they're evolutions towards the terminal velocity, but one's exponential and one's determined by this hyperbolic tangent here. Again, if you want to figure out what the terminal velocity is, that's a simple problem, because you can just figure it out by equating the drag force and the gravity force when you're at the terminal velocity, when you're in that equilibrium between the two forces, because you're not getting any faster or slower. And if you do that, you get this little expression here for the terminal velocity. Again, it ends up being kind of a comparison between the gravitational force, so the greater the mass, the higher the terminal velocity, and the quadratic drag force. The greater the quadratic drag coefficient C, then the lower the terminal velocity. So it's the same sort of comparison. There's again a time constant of this evolution towards the terminal velocity. An expression for the time constant is this little guy here. Okay, so this we're also going to solve analytically, numerically. As an example of numerically solving ordinary differential equation. Again, we're going to solve it in a way that is very general, and we can change the differential equation and solve a different problem very straightforwardly, easily. In this case, I said for linear drag, the step from one-dimensional falling motion to two-dimensional projectile motion is a big complication in the analytical solution of the problem, because the drag force couples horizontal and vertical motion. In the case of quadratic drag force, the step from one-dimensional vertical motion to two-dimensional projectile motion with a drag force is actually an unsolved problem analytically. So there is no analytical solution that we know of to this problem. And again, it's related to the coupling that the drag force causes between the otherwise separable horizontal and vertical motion. So that this truly is a problem that can't be solved analytically. Okay, this now I'm going to make a couple of general comments about the analytical approach and the numerical approach, and then we'll look at some details of the numerical approach and how we're going to code up the numerical approach. But let me say something on the analytical approach. On the analytical side, there are some differential equations that are analytically solvable, for example, by just separating on the left and right hand side of the equal sign, the variables. You just separate the variables. So free fall in the absence of air drag, separable equation, and then you can just integrate it. You integrate the left-hand side and right-hand side. So that type of analytical differential equation, straightforward to solve. There are lots of other methods for solving differential equations analytically. There's a whole, I asked ChatGPT this, and I gave 20 different methods for solving problems analytically. It's just a small, huge collection of analytical methods that work in these little corners of the space of differential equations. One of them that we often use in physics is kind of a trial solution. This is also a relatively easy one. You pick a solution that you think matches the problem, you try that solution out, and you put it into the differential equation, and if it works, you found the solution. And then you can tailor that trial solution to your particular initial conditions. Notwithstanding all that, right, most differential equations of real life problems can't be solved analytically. So the problem with analytical approach is it's piecemeal. You've got to learn all these different techniques if you want to solve a lot of differential equations. And also, they don't work in general on most real life physical problems. Numerical approach. Well, one thing that's nice about the numerical approach is that there's really just a general approach to all ordinary differential equations. So you're not picking out of some menu of different analytical approaches. There's just a general approach for solving numerically solving an ordinary differential equation, and it's the same approach whether it's first order, second order. We don't beat them in physics really, but higher order, or it's linear or non-linear, or all the other sort of variants of differential equations. It's going to be the same computational numerical approach. So that's a huge virtue to it because we just got to learn one approach. And here it is just summarized. So we talked about this before. We're going to take continuous smooth time and we're going to discretize it into little ticks or little steps through time, and a finite number of steps through time. So that's an important point. One thing that we're going to do that I haven't talked about before is that we will take our ordinary differential equation that we want to solve, and we're going to reduce it to just first order differential equations. So just to be concrete, the equation of motion is a second order differential equation. It has a second order differential with respect to time of the position of a particle. So that's a second order differential equation. We would, in numerically solving the second order differential equation, we would break that into two first order differential equations. I'm going to show you how to do that. So it might sound a bit abstract, breaking second order differential equations into first order differential equations, but it'll break into two first order differential equations. I did put here in a graded an example. So you can reduce that equation of motion, free fall under gravity, second order differential equation, into a pair of first order differential equations. So they're first order differentials of the old variable in the second order equation, that's the position variable, and a newly introduced variable, that's the velocity, which is in the second of the first order differential equation. So this is the sort of classic example, a simple example of this breakdown of a second order differential equation into two first order differential equations. So we're always going to do that. And that's part of the general method. And it might seem a bit abstract and a bit kind of wide, but we'll see that it's actually, in our application, rather straightforward. And actually, we kind of already did it. I'll show you on the next slide, we already did it. Once you've done that, then armed with that, and knowing the initial conditions for the two variables, so position and velocity, say, and using the Taylor expansion, Taylor approximation, you can calculate the new position and velocities for the next tick, the future tick, based on the current position and velocities for the current tick, based on these two ordinary first order differential equations. That's the whole method. And you just do that over and over again until your heart's content or whatever. What's interesting is, so I don't know if that method, I remember that method sounding like this reduction of higher order differential equations into first order differential equations, introducing new variables, all sounded a bit abstract to me, but actually intuition in the second class of the semester led us to do that. Remember, in the second class of the semester, we solved the problem of the falling body numerically based on knowing the initial position velocity of the falling body, based on discretizing time in lots of little steps, and based on calculating the future position and velocity of the falling body for the next tick from the current velocity and position at the current tick. And this was the code that we used in lecture 2. And this calculation of the future position by adding on this little increment to the current position, and the future velocity by adding on this little increment to the current velocity, is at its heart, at its core, the using this approach of breaking the second order equation of motion down into two separate first order equations, differential equations, and using those to incrementally update the position and velocity. So we were doing this, although we didn't use those words, we were doing this in intuition, that is to just calculate the incrementally the position and velocity, not realizing we were breaking a second order differential equation down to two first orders. Okay. So this method we used here, this isn't very general code. It was really just written for this one problem of the 40 body. So we want to improve and make it a general code, but it does include all the ingredients that we just talked about the general method for solving ordinary differential equations numerically, discretizing time, separating a second order into two first orders. We're using the Taylor expansion or approximation to step from time interval to time interval. We're using that here, and we're repeating the same process over and over again and building the trajectory of the particle out of the original initial conditions for the particle. All that's going on in there. Okay. I'm going to go soon-ish to two codes that I've written. One for solving the simplest case of a first order differential equation numerically in a kind of general way, and then the one for solving a second order differential equation generally. As I say, in physics, we only just about only really meet first order and second order differential equations. So we're really solving, this is a foundation for solving all the sort of ordinary differential equations we'll meet in physics. Right up at the top, y prime equals some function of y and time is kind of how I think of a general first order differential equation. So time is the independent variable. Y is the dependent variable. Y prime is its differential, as my notation there. And so this is a first order differential equation, first order differential of y prime. And in general, that first order differential could equal sort of any function of the coordinates that we got, the variables that we got, which are position y and time t. And so this method can solve any f of y and t. So it's just going to solve all the first order differential equations. So the classic one we've been working with a first order differential equation is that the differential of the velocity, acceleration, first order differential of velocity is equal to acceleration of gravity. So that's a simple example of this. So the way that we're going to code that up is knowing that from our work on Taylor approximation, we can compute the velocity at a time tick vi plus 1. So that's a tick of the clock, I plus 1, from the velocity at from the velocity at the previous tick, v subscript I, plus the differential of that velocity times the duration of the tick. So this is the first order Taylor expansion. When we talked about the first order, the Taylor expansion before, we said that f of x can be written as f of 0, say the function of the origin, plus a correction. That's the first order differential at the origin times the distance from the origin, plus another correction, this is second order of correction, which is second order differential, times the interval from the origin to the location of the functions squared, and so on, a third order, a fourth order, and fifth order, and so on. So there was a whole Taylor expansion for writing f of x in terms of f of 0. Now we just change the language to v of I plus 1 in terms of v of I. But again, the first term, the first order Taylor expansion is it just depends on the rate of change of v and I, which is the acceleration, which is what our ordinary differential equation is. So we're going to use this one equation here, the Taylor expansion, just the first two terms of it, just the first order Taylor expansion, with a expression for this differential v of I prime that's specified by our particular ordinary differential equation. And the one I'm picking in red here is just, to start with, is just free fall on gravity, where the rate of change of the velocity is equal to the acceleration of gravity. So that's the procedure that we're going to follow. And then this procedure is going to allow us to calculate vi plus 1 from vi. And so if we know v, let's call it v naught, at time t naught, then we can calculate v1 at time t1, v2 at time t2. We can work our way through time horizontally here, incrementing the velocity vertically here by these little increments that I've specified here that are the product of the rate of change of the velocity, the dependent function, times the interval in time. So that's all. This is a picture of our method, and these are the two equations that we need for our method. And this will work for any any first order differential equation. That's the powerful bit about it. If we write a code for this, you have a different differential equation, you just have to change what's here. It does remind us that this is a approximate method, right? It's not going to be an exact method. There's going to be approximations that are made because we're making the approximation just using the first two terms in the Taylor expansion. So we're just using a Taylor approximation of first order. But what's important about recognizing that we're doing that is it tells you how to estimate the errors that you would make in just taking the first term in the Taylor expansion, because you can look at the second term in this Taylor expansion and you could ask, well, what sort of error does that make? And so that's what I did down here. In this formula here, which I said is approximate, we're omitting terms of order delta t squared and higher powers. Delta t squared will dominate. And so that's the scale of the error in one step of our process. The scale of the error over the whole time region that we're going to calculate, that actually goes as delta t squared times the fact divided by delta t, and becomes just delta t because we need a number of ticks that is in proportion to delta t. So if you make more ticks, which make the errors in an individual step shrink, the downside is that you've made more ticks, which means you have to do that calculation, which has a small error, more times. And the end result is that the error scales for the overall trajectory is delta t. The error on a single step scales as delta t squared. If you make it delta t smaller, your numerical calculation, the error gets smaller by delta t squared, square the time t. But if you, the error on the whole trajectory, by the time the projectile hits the ground, that squares as delta t. So if you make delta t smaller, the error only gets linearly small. Okay. So that's one dimensional problem. Sorry, a first order differential equation. I want to just say a little bit of how we set up the solution to a second order case, which is the other case that Wim made. As I said, we're going to break it into two first order differential equations. These are on the left and the right here, just two different examples of doing that. On the left hand side, this is the free fall case, but now I'm thinking of a second order differential equation where I'm going to solve for the position y of the falling body. And here's another case of a second order differential equation. This is a second order differential equation for, say, a mass on a spring oscillating to and fro. Again, this is a different equation, but I've listed the procedure for solving the oscillator versus solving free fall, and they're exactly the same procedures. We start with a second order differential equation, and we're going to introduce a new variable that is the differential of the dependent variable in our equation of motion. So the independent variable in the equations of motion here are time. The dependent variable is y, and the new variable is going to be the differential of y. Well, that's velocity v. So it's not like we're introducing some, unknown, weird, abstract variable. We're just going to introduce, in this case, what is definitely a known concrete variable. It's the velocity y. It's the first order differential of the position. It's the velocity v, which is first order differential of the position y. That's one of our two differential equations. We said we were going to break the second order into two first order. One of them is the introduction of the new variable that v equals y prime. That's this guy here. Then to get the other of the pair of first order differential equations by this introduction of a new variable, you just substitute the new variable, which is v, into the original second order differential equation. So I'm going to replace second order differential of y by the first order differential of v. And that's our second equation. So this is the pair of first order ordinary differential equations that this second order Pauling body reduces to. And this is the same thing for the reduction of the oscillator differential equation into two first order differential equations. So there's nothing really abstract about it. As soon as you start thinking about these concrete cases, where you just learn that we're just beginning to talk in the language of v and y for the motion of the particle, which is exactly how we were led by our intuition when in class number 2 we solved the problem. Okay, so it's a matter of solving these. The new bit that I want to introduce is the way we're going to code these up. So the way that we're going to code up our two variables, we've got y, position, v, velocity, is we're going to code those as a variable. I call it uppercase y, but it's a two-element, two-component vector. The upper component is the position, and the lower component is the velocity. So this is going to be our new two-element variable that incorporates both the variables that we've introduced in the problem. And that's the way we're going to code it. It's very convenient in Python where you can handle vectors. The differential equations. This here is the pair of differential equations. How I'm going to code up the pair of differential equations. So the differential equations will be the differential of this variable, two-element variable. The differential of the upper element, the position, is y prime, and it equals v. And the differential of the lower component, that's v prime, and that equals minus g. So this is my vector notation of the two differential equations. So I've introduced here the language for expressing the two variables and a language for expressing the differential equations that is very handy for the Python coding solving of this particular problem. And it's exactly the same over here, right? The same two-component vector that I introduced. Same idea about representing the ordinary differential equations like this. The only difference here is that now, well, v is still first order differential of y prime, but v prime, the rate of change of v, is now determined by how much you stretch the spring constant mass of the spring. This procedure of writing everything as one first order differential equations is completely generalizable from the first order that we talked about, the second order that we're just talking about, to higher orders, third, fourth orders, and more. It's just we're not going to really meet them. It's a very, very general approach. If we use this approach, the way that you would solve a second order differential equation, so at top in black, y double prime equals some function of y prime, and time. That's my general expression for a second order differential equation. So the independent variable is time. The dependent variable is y. Second order means it can depend on the first order differential and the second order differential of y. And the general form of the second order differential is that the second order differential can equal some function of time, the independent variable, y, the independent variable, and the rate of change of y prime. So that's a general expression. and that's solves every one of those. And this is the particular example of the Falling body in red here. So I set up how I'm going to do the calculation of the code here for the example in red. Again, going to break time down into discrete steps, and we're going to step through time, calculating the future value of the variables from the current values of the variables. We're going to use the Taylor expansion in combination with the particular ordinary differential equation we're solving. So the Taylor expansion, again, it says to first order Taylor expansion says if you want that function f of x, some location x, it's equal to the function's value at the origin, f of 0, plus a correction from the first order differential. So f prime of 0, the differential of f at 0 times the interval to where you want the function. In our language, it's that y at the clock tick I plus 1 equals y at the clock tick I plus this correction, which is the product of the differential of the function evaluated at I times the interval to I plus 1. We need to evaluate this, the rate of change of that variable y. Its differential, remember, it's a two-component vector with the two variables as the two components, and those are specified by the two ordinary differential equations. So here's the variable y was equal to the rate of change of y, variable v was equal to the rate of change of y prime, and here's the fact that rate of change of the velocity is determined by the acceleration of gravity. And then if you just repeat and repeat and repeat, you can reconstruct as a function of time horizontally how the position y in the how that evolves, how the velocity v evolves based on this calculation here. So again, just step through time, looping through these two lines, evolving the position at the time. Same comment about the errors. The beauty of this is that we're using a Taylor expansion, so we know how to assess the uncertainties, the errors that we make when we're doing these approximations, these numerical calculations. And the error for an individual step goes as the square of the time interval. So make the time interval half as big, you reduce the error by a factor of 4, but the error on the overall interval, the whole flight time, say, of a projectile, that goes as the time interval. So if you reduce the time interval by a factor of 2, you reduce the error on the whole path by a factor of 2. So that's very useful to know how to understand the uncertainties you're introducing. Okay, let me go to code. So this is my physics 508 directory, and I put two new things in here. I put this free fall velocity and this free fall position. Those are two cases of the one first order, second order differential equations we've been talking about. I'm calling, I haven't used the word, Euler, Swiss mathematician, who invented this method. Kind of we invented this method as well. In class number 2, we just dreamt up this method. We were just 300 years too late. But he first invented this method. He invented a lot of the symbols that come with this method, like delta t for a time interval. That's thanks to Euler. And so this method is called the Euler method, and that's what we're going to be using to solve the first order velocity versus time problem of a falling body and the second order position versus time of a falling body. Let's start with the first order. This one here. And I'm going to, I wasn't going to code this up live, but I might change it a little bit as we work through it. let me walk through some of these cells. I've obviously got to make this larger. I'm at the front and I can't even see it. Why can't I? Okay. Is that large enough up towards the back? Or should I make it larger? It's okay. Well, we're going to use vectors, for example. We need NumP. We're going to plot our results. We need matplotlib. That's obvious. We've done that before. I'm going to make this rather general and rather flexible. I'm going to define two functions. And then I will just be calling the functions. Like in the last lecture, we defined the function for the logistic map. It's a way of writing the code for the function once and then just calling the function rather than over and over again writing the code. The two functions correspond to one, an implementation of the differential equation that we're solving, and the other one is an implementation of first order Taylor approximation. So that's what these two functions represent. And this code, just to stress it, this is solving the first order differential equation for a falling body without drag, solving the velocity of the falling body without drag. So it's first order differential equation. The differential equation is represented by this function here. So if you look at the arguments of this, my user-defined function here, I pass the coordinates, position and time for the particle. That's the VI and TI. That I is my index of the discrete time and the discrete velocities. So I pass the current coordinates, and it's going to return based on the law of gravity and the laws of motion, based on the ordinary differential equation describing the problem, the differential. So it represents the differential equation. It returns dv dt given the current vi ti. So that's coding the differential equation. This is coding the Taylor approximation. When I call this function, I pass a number of arguments. I passed more arguments actually than I needed because I wanted to make this general that in other cases I may need more arguments. But I'm passing the coordinates again, VITI. I'm passing the time derivative. Actually, what I just said about not using all of this, that's wrong. I pass the dependent and independent variable, VITI. I pass the time interval, dt, the length of time of the tick. And I pass, what's this guy here? This guy here is going to be the name of a function. And it's going to be the name of the function describing the ordinary differential equation. So I would pass, this is going to be a string name that is going to correspond, say, to this function from there. So those are the arguments. That's everything that you need for the first order Taylor approximation. To calculate VI plus 1 from VI, you're going to take VI and you're going to add a little increment, which is the product of the time interval and their differential of VI, the rate at which it's changing. So this is first order Taylor expansion. And I'm returning the VI plus 1, the new velocity. Does that make sense? So I did it this way because we're always going to use the same Euler method for solving the problem. So we're always going to be calling this. And then if we use a different differential equation, maybe if I add drag, I could just add a new function here, use a function that would include the drag. Okay, so That's just defining, library functions and user functions in that cell, nothing beyond that. This cell next, this is just for me, and I come back to that. These are just some parameters to discretize time. I've got to do that, where I've got to make choices about kind of the ticks, the steps in time, and the range in time. So in this calculation, I'm going to have 1,000 total ticks, and each tick is separated by 100th of a second. And so this is 10 seconds worth of time in total. So when I calculate this, this will be 10 seconds, total time range. I need a couple of quantities to solve the freefall problem. I need the acceleration of gravity, so I've obviously defined that there. I also need the initial velocity of the body, whether it's going up and down or at rest, and how fast. So that's G naught. In this example, I'm just starting the body at rest. So that's straightforward. It's just initial conditions, acceleration of gravity, and my choices about discretizing time. And obviously there, in my choices about discretizing time, I could make the calculation we know more accurate and make delta t smaller, make it a millisecond, not 10 milliseconds. But the cost is I'd have to go use more computer time to follow the same trajectory of the particle, or I could make it coarser. I could go to 100 milliseconds, but the cost is, well, I need less computer time, but it'd be less accurate. So, if you are doing this in practice, you worry a lot about the choice of this number, because this number is the big compromise that you make between accuracy and expensive computing. Okay. The whole calculation is done in this cell. The whole solution of the ordinary differential equation is done in this cell. So that's the remarkable thing about this. Upstairs here, the first two lines, they're not even really the calculation. They're just kind of setting up the calculation. I need my dependent variable. I need my independent variable, time. And if you remember Lin space, we made it. It creates a equal step sequence of equal intervals of a sum range, and that's how I'm going to create the discrete time. So discrete time is going to run from 0 to 10 seconds, we said, TF, with 1,000 little increment steps. So that's defined time. I'm going to, what I will call initialize or declare a vector v that I'm going to fill with the, I'm going to fill the elements of it with the velocity as a function of time. But here I'm just initially, I'm initializing it all to 0. So it's the same size array, also size n. That's indicated here, but it's just going to be filled with zeros, and we've got to then go and calculate it. So that's now I've got two variables. This is my proxy for continuous variables t and v. I've got discrete variables t and v. Right. So we know the velocity at time 0. You've got to have an initial condition. This is the velocity time 0. So I set the array element of v, the 0th array element to be v naught. And in this case, we're setting it to be a rest, but we could have picked any number going up, going down, whatever. And then I'm going to do the calculation of all the other values for the velocity by calculating the one at, here my label is j plus 1, the tick j plus 1, from the velocity at the tick j, based on calling the Euler the user function, which uses the Taylor approximation, and which itself uses the free fall function for the ordinary differential equation to specify the rate of change of the variable velocity. So this is my one line that really does the calculation. And we just buzz through that 1,000 times, stepping through time, calculating the values of the. Any questions on that? So you see here, once I've set it up, it's very compact to actually solve the problem. Okay, so we did the calculation. So now, at the end of this cell, we've now got these two arrays, our proxies for the independent variable time, the dependent variable velocity, and we can look at velocity versus time. So let's just make a plot of velocity versus time. And that's this very last cell here. So there's no calculations here. My first call to plot, where I'm going to plot blue circles, is to plot my numerical calculation of V versus T. So blue, they look like a thick blue line, but they're 1,000 blue circles, dots. As a comparison, look, I know the analytical solution here is given by this free fall law for the velocity. And so I'm just following the expression for the free fall law as a red line. And that's the red line here. And so that's just a check, right? I didn't mess up in my calculation, numerical calculation with those two user functions. The red line and the green dots are overlapping. We see the velocity, of course, we know what to expect. Over these 10 seconds, the velocity should grow linearly with a slope that is the acceleration of gravity. So it grows to 98 meters per second over these 10 seconds because it's growing 9.8 meters per second every second. That's the acceleration of gravity. And so that was easy and straightforward enough. Any questions on that? So the nice thing about this way of set it up this time, which would be a criticism about the way I solved the problem in lecture 2, is that this is a very flexible approach to solving the problem of not just this differential equation, free fall, but all sorts of other differential equations, say with linear drag, say with quadratic drag, or maybe we're worrying about subsonic to supersonic transition that's called transonic. We could invent any sort of problem to try and solve it. So let me just show you. Maybe I'll supplement the differential equation with an extra term. So to gravity acting downwards, the opposite direction, I'm going to add this term here. This term here is quadratic drag. So this is VI squared. So that's the velocity squared, that's quadratic drag. Quadratic drag in the equation of motion was multiplied by a coefficient C, quadratic drag coefficient. That's going to be part of this variable here, C over M. When we wrote down our equation of motion, we had mass times acceleration on the right-hand side. The equation I'm solving here is just acceleration equals the sum of the forces divided by the mass. So this is really C over the mass, C over M. I've defined one quantity to represent that. It's just that here I don't actually need to know the value of C or the net value of M to solve the problem. What's only important is the ratio of C to M that determines the effects of drag. It's just that, if you make the mass bigger, you're going to reduce the drag. If you make the mass smaller, coefficient of friction bigger, you're going to make the drag larger. And so only the ratio counts. So I've added in this term here. Now that means I've got to define what C over M is, this equation, this line here, and I've also commented out, defines that equation. This is I took an example of a baseball. I think I took an example of baseball, and I'm dividing the quadratic drag coefficient for a baseball by the mass of the baseball, 145 grams, so about 0.15 kilograms. I calculated the coefficient of friction for the baseball based on a formula that I actually gave you. We didn't talk much about it when I introduced quadratic drag and linear drag. So I used this equation. So all you need to understand this number here, this pair of numbers here that is on this line as a comment, but this is the quantity that's going to characterize the roller drag. The roller drag will scale this quantity. We've now defined it. I also, just so that we understand a few things, once you've specified that quantity, the square root of g over that quantity is actually the terminal velocity, and the square root of 1 over the product of g and that quantity is the time constant for achieving, sort of evolving to the terminal velocity. So I'll just print those out. So we're going to run this program again. I hope I did run that. Yeah. I'm going to run this. Well, what's gone wrong? Oh. Yeah, it probably didn't like me doing C over M. It might not have liked me defining those two functions and printing them on the same line, I suspect. I don't exactly know what it was thinking, but empirically that fixed it. Terminal velocity of that baseball is 32, roughly 32 meters per second, it says. This is the time to reach terminal velocity. I don't quite, oh, but I've done that wrong. Okay, so this is a good example, right? I look at that number and I think, well, I don't think it takes a baseball less than 1 millisecond to achieve terminal velocity. I just don't feel that that's right. So let's try actually dividing by g and c over f. And then we get what might be, I don't really know either, but it sounds more plausible. 10 seconds of free fall to reach terminal velocity at 31 meters per second. But even that doesn't seem right because I'm missing square root this thing. This line. Well, I'll never forget it. Okay, I think this makes more sense. These are the correct expressions for the terminal velocity and the time constant to reach terminal velocity. And 32 meters per second and a few seconds after dropping the ball sounds sensible. So those are reference points for our calculation of free fall. I didn't have to change anything here. I mean, I modified my free fall ordinary differential equation to make it actually no longer free fall, but with a drag force. But I just rerun the same code and then I can replot. And here we've got the result. And so this is free fall in red. In blue is my numerical calculation of the baseball's fall in the presence of drag. We said that terminal velocity is about 30 meters per second, looks to be about right here. We said that the time constant or reaching terminal velocity was a few seconds. That seems to be about right here. So you've just seen how once you've got the structures of the code, it's very easy maybe to write. If I had a little bit more time, I would have written a new function, drag for rather than free for. I could have written a function quadratic drag for, linear drag for. We could have had one for supersonic drag for or something. You can write these additional functions and solve this whole world of different problems. Any questions on that? Okay, I want to, in the last 5 minutes, make sure.
Actually, could
Yeah.
you scroll up just
Yeah.
one student?
This bit or
The code block breakdown.
oh yeah. Oh, right below the graph.
Yeah, this one right here.
This one.
Okay, that makes sense. Thank you. Sorry, it's all good.
Okay, good. Let's go on. So I have another code for the second order. Yes.
So just linear drag is the coefficient still just C over?
No, I put it in the slides, but it's way back. Coefficient was called B then,
Okay,
rather than C. But it's just the drag force is BV rather than BV CV squared.
okay, right.
If you, so you might have a B over M or something. Yeah. Okay, so this is the code, the equivalent code I wrote to solve the problem of second order differential equation rather than first order differential equation. So this is solving for the position of a free fall body rather than the velocity. And I think the code is, I just took the previous code and added to it to do the second order differential equation. And because of the way I'd structured the first order differential equations, it was easy to modify it. But I want to show you the key modifications. So here we remember the two user functions for the free fall and the for the differential equation and for the Taylor approximation. The difference now is that we said for second order differentiation, a quantity variable representing the dependent variables, y and v, is going to be a two-element vector rather than just a single variable velocity v. So now we got dependent variables v and y. So that's a key difference here. And maybe let me show you where I define that first, and then I'll talk about the functions. So for example, I'm now having to define the initial position and velocity in this cell here. That is a difference. More importantly, though, if we go and look at this cell here, here's my definition within space of the time intervals, ticks. Here's my definition of this, I'll call it meta variable y, that has these two elements that are position and velocity. This meta variable y is a 2 by n array, 2 for the two variables y and v, and n for the n ticks of time. So this has changed to be a two-dimensional array, 2 by n, rather than last problem code a one-dimensional array, because now this meta variable contains two variables, y and v, rather than the single variable. So here you can see I'm filling two different positions with the initial velocity and the initial position. So that's the difference. That means that backing up to the function, these two functions, yeah. This looks exactly the same. This is exactly the same Euler function. It's just that now when it gets used, yi will be a two-element vector. And it will be calculating the two-element vector at the next time tip. So the function is the same, but the nature of the variable coming at yn and going out at yi plus 1 is now different. It's a two-element vector containing velocity and position. This free fall is now different. The free fall second order differential equation we said would be represented by two first order differential equations. One is just the definition of the new variable. So that's this guy here. But the differential of y, the position y, is equal to, sorry, the differential of the velocity, differential of the position is going to be equal to, differential of position is equal to the velocity. This is the velocity in this two-element array. So this y1 is a v. And then the differential of v, which is the second element in the array, the one here, that's equal to the acceleration of gravity. So this is the second order differential equation. So these two comments are to tell you what differential equations these represent. So this has been extended to contain two lines for two differential equations, the two first order differential equations that we broke our second order differential equation into. And that's basically the difference that I made. Let me just run it, because I'm always running out of time. Run all. The cell that contains the coding following the trajectory of the particle has not changed at all. The Euler function didn't change at all. There was a little change in the free fall function because it's now coding two ordinary differential equations. And there's a little change in the initial conditions and that meta variable uppercase y that contains velocity and position. But now I've run all that and I've solved for, in blue, I'm plotting position versus time. So this is the position variable versus time. And in red, I'm just doing the analytical solution for position versus time, the quadratic equation. And so we see that that also was able to, our numerical calculation, we checked our numerical calculation on that analytical one.